So this is my section 5.1 video retake for the question 53 from section 5.1, and this question revolves around pretty much taking a given sequence and then determining its limit to show whether that sequence diverges or converges, and if it does converge, we should be able to find its limit on what it converges to. And just like the previous 4.3 section video, I'm going to kind of go over what are the key points in 5.1 before I get into the question, because that is the main point of this. Like, we want to know like what makes this different in terms of figuring out like which equations to use, etc. So pretty much the first thing that we start off with in this is we start by observing like what a sequence is, like whether it's geometric or arithmetic. Only difference is arithmetic sequences have like a constant difference, whereas a geometric sequence has like a ratio difference from the consecutive terms that makes its differentiation. And moving like forward from that, what we're trying to do is pretty much find the limit of a given sequence, because if we are to find the limit, that would tell us whether the sequence itself is converging onto a set point, or at least to an asymptote, or if it is diverging in nature. So what that pretty much means is if it's like close to a finite number, and like say the sequence is a of n, right? So like as n like grows, like as the sequence progresses, technically, like if a of n itself is closing in on like 0 or a limit, then it is a convergent sequence, and we can actually find the limit, which is L of the sequence, and we can write that the limit of, while n approaches infinity, the limit of the function a of n actually equals L, which is the limit, or like what it converges onto. And of course, like if it like is expanding, like if the a of n function is not really approaching a defined point or a limit, then we say that it is diverging. And how we kind of go through this is we can pretty much given like an a of n function, like we can take an approximation function, which is the a of n plus 1 function, and then use that to approximate the actual function, because if it is a continuous function, a of n plus 1 should also be converging in on the same point if it is a convergent series. So I'm going to start the actual problem now. The problem again is a sub n equals n prime squared, so n prime in parentheses all squared, over 2n in parentheses, and then the factorial of that. So sorry, I think I said that entire thing wrong. I'm just gonna say it again. Again, for clarification, it's a sub n equals, in parentheses, n factorial, and then close parentheses, squared all over parentheses 2n close parentheses factorial. So the first thing we're going to do is we have our a of n function. Let's find a of n plus 1. So a of n plus 1 equals n plus 1 factorial squared over 2 2n plus 2. 2n plus 2 because we have to distribute that 2 since we're putting in n plus 1 for that. And now what we do is we can use the equation an plus 1 over an to try to simplify that down to at least find the power of the denominator to tell if to kind of get to that point where we can actually conduct a limit test, I guess. So just in the term of the process, in the way of the process, I'm going to do a sub n plus 1 over a sub n equals, so all of this, which is n plus 1 factorial squared over 2n plus 2 all over n factorial squared over 2n factorial. So from here, we can pretty much just keep, change, flip, simplify this down to whatever, this, like an easier term to find the limit for. So if we keep the, or sorry, not simplify it down, but we can just multiply it by its like reciprocal, or sorry, it is simplifying it down, but I'll just write the math and I'll show you. It's the process we went through in class. So we do plus 1 factorial squared over 2n plus 2 times 2n over n factorial squared. And then once we simplify that down, squares cancel out. Or what we can do. Would equal Okay, so sorry, it took me a while to think that through, but once we do this, we can cancel out the squares from the n plus 1 factorial squared on the numerator and then the n factorial squared on the denominator. And we can also, since it's n plus 1 factorial, and then the denominator of the other term is just n factorial, the n factorial actually cancels out at the bottom of the second term, and we're just left with a singular n factorial on the numerator of this. The next thing that happens is we can simplify down the 2n and the 2n plus 2. So how we do that is okay. So I realized why I was tripping out. Like I was just blanking. I actually forgot to write in the n factorial part about this. I forgot to include the n factorial for the top and the bottom term. So now I have n plus 1 factorial squared over 2n plus 2, all of that as a factorial, times 2n factorial divided by n factorial squared. So I simplified the numerator already of the top left to just n prime, and then now we're going to try to cancel out the numerator of the second term, so we're just left with the denominator. And what we have here is it's 2n, all of that in one factorial, times the new denominator, which is 2n plus 2, but it's all of that factorial as well. So I'm thinking the way that we solve this would be we can separate the 2n plus 2 whole factorial into multiple terms and cancel out the 2n factorial. So since, like how I'm thinking about it is 2n factorial, say n is 3, the denominator would be 8 factorial, so it would just be 8 factorial times 7 factorial on the bottom, which is which would just be n plus 1, n plus 2, so say it's 3, it's 6 factorial, this would be I think this is actually recurring terms. I think it would keep going, actually. Like, it would go up to, like, the denominator. So the simplified term that I got to was n factorial over n plus 1 times n plus 2 times n plus 3 times n plus 4. Like, it goes all the way up to 2 to the power of n, I believe, because with the example that I gave where n equals 3, like, the way that would work is if we did cancel out if we did plug it in, then the numerator of the top right term would be 6 factorial and the bottom term would be 8 factorial. So the only terms that would be remaining would be the 8 factorial, or it would be the 8 times, like, it would just be the, like, 8 times 7, because the 6 factorial is where it will cancel out that numerator. So, like, I'm not sure how to write that, because again, it would need to be actually, it does go up to 2 to the power of n, actually, at all times, because even if you did plug in like 4 or whatever, actually, never mind. Sorry, I'm trying to think this through and find some notes. Actually, I don't think we need to come down to like a definitive value. I think we can take the approximation, and in this case, it does actually go up to 2 to the power of n. So it would be n plus 1 times n plus 2 all the way to 2 to the power of n. And that would be the upper range of the approximation. So I think from here, what we can say is that a sub n plus 1 over a sub n is less than 1 over 2 to the power of n, actually, because what we're doing here is, again, we're trying to find, I guess, like a base function using the approximation of a n plus 1. And from there, like, first of all, like, the fact that the function that we found, the 1 over 2 to the power of n, it shows that it does converge because of the p, like, ratio. I think, 1 second, sorry, I might be jumping the gun. Well, I know that it converges because n exponentially grows and it just goes towards the asymptote of 0. So I'm gonna say it I'm gonna say it converges. I'm gonna keep thinking about why, like the actual like why I can use that approximation, because I know you would want to hear that. But I'm gonna go ahead and do the limit test to test if it approaches 0, or what value it approaches, which I do think it's 0 again because I've seen this function before actually. Um, limit of n goes to infinity, a sub n equals the limit of n going to infinity of the function we just found, which is 1 over 2 to the power of n, and I think that's just 0. Yeah, I don't think you can value, like, I think because of, I think L'Hopital's rule, like it would just be 0, the limit of an equals 0, and that again shows that again proves that it converges by the limit test. Yeah, so I'm not sure that it's I'm not sure if this is all we need to show, but I do believe that it does converge. And like, again, this entire chapter pretty much talks about determining the convergences and then finding the limits based on whether it converges or not. And again, I'm trying to find the exact wording for this, but yeah, again, like this entire subsection, section 5.1, pretty much was about like sequences in the first place, like figuring out whether they are convergent or not. If they are, we can find where it converges by taking the limit of that function. And other than that, when we are doing that limit test, the thing that we have to remember is that the limit as n goes to infinity of a sub n equals L, so that the a sub n function converges on limit L, or the value of L. And other than that, there are the algebraic limit laws that we went over together as well. There is, what else? There's the squeeze theorem as well, which we did go through as well. That just states, or that just shows, like, if there are three functions, a sub n, b sub n, c sub n, and it's in like the increasing order of a sub n is less than or equal to b sub n, which is less than or equal to c sub n, then there exists a value, or sorry, I'm saying this correct, completely butchered. Sorry, where did I write this? Yes, sorry. So the squeeze theorem, again, it just talks about finding an integer n, where when you put the sequences a sub n is less than or equal to b sub n, less than or equal to c sub n, there exists a real number L where the limit of a sub n, given that it is converging, equals L, and that also equals the limit of the c sub n function. then the B sub n function has to converge. So like the squeeze theorem pretty much talks about like proving the limit, like proving the convergence of two bound functions a sub n and c sub n, finding that limit L, the number that they're converging towards, and saying that if b sub n is a function that is bound by the two functions, then it will also approach the same limit as them, which is limit L. And I think that is pretty much it for subsection 5.1. And yeah, thank you.